developing next-generation research and technology, facilitating connections between AFRL industry and academia, unlocking innovation through a culture of collaboration. This is the AFRL Regional Network Midwest.
The Air Force and the Space Force are interested in minimally invasive wearable sensors. Having these sensors that could detect biomolecules or other biomarkers of health and performance could help to increase the performance and monitor the health of these airmen and guardians when they are on a mission. So microneedles are tiny microneedles that are about 1 millimeter in height and anywhere from 200 to 300 microns in diameter at the base to even a millimeter diameter at the base. So microneedles come in many different forms. There are microneedles that dissolve to deliver drugs. There are microneedles that can absorb analytes for offline analysis. And the microneedles that AFRL is currently interested in are conductive microneedles that will be functionalized with an electrochemical sensor. And they will actually send signals back to the electronics to measure analytes in the human. Thanks to the first increment and 6-month period of performance on this project, we were able to achieve additional profiles, including sort of torpedo or bullet or straight type ones with a sharp tip, as well as tissue interlocking ones that have a bulb or spade shape, as well as just normal tapered straight microneedles. We also modified our printer with an airbrush tip so that we could get microneedle arrays with a very tight spacing of 1.25 millimeters, which is very close to what AFRL RHBCO already targets. In addition, we refined our process for improved uniformity here across a line of 8 microneedles, which when analyzed have a coefficient of variation of 2% in height and 12.45% in width at 600 microns high. Part of that refinement was a recognition that our process really needed 2 phases, a positive or piling phase where the extruded material is beyond the inner diameter of the nozzle, and a negative and drawing phase where it necks and eventually breaks. We call this Continuously Variable Stacked Extrusion and applied for a patent. In order to integrate our microneedles to actual devices, we had to create a post-processing script that would insert the microneedles. We start with an STL file of our device. Within that device are some marks that tell where the microneedle would go. We load this into our slicing program, generate the G-code, and then process that with our Python script. This allows us to create these devices with microneedles on top and that fit into a normal USB. Finally, we confirmed that the conductive material we used for the microneedles was biocompatible. So this increment, we continue to address the microneedle package design, how it's unreliable and difficult to scale. But now we are focusing on 2 main issues that really get at the heart of these individually metallized microneedles that can be assigned to different channels. And so part of that is metallization, which we have some decent results from, and the multi-material printing. And so we have 2 main goals for this increment. One is to develop a nickel metal coating protocol that offers complete metallization so that there's no gaps and that there's no protruding flakes or leaves or clusters around, so you can see how uneven these microneedles are. Our protocol should be more refined than that. It's going to be based on maintaining a specific current, and that the metallization should have good adhesion to the underlying polymer so that no residual metal ends up in the skin. To facilitate the individual metallization, that's where our multi-material printing comes in, where we're using conductive and non-conductive materials. And to get the high resolution, we're actually building a new system that actually prints these in a way that is superior to what we achieved last increment using our engine HR.
Through the Midwest Hub and this partnership with Dr. Pirlo and UD, we're able to iteratively, very rapidly develop platforms over here at UD and transition them to our lab he can print them over here, as well as he can send a file that we can print on our, at our facilities and be able to put our sensors down and evaluate the performance as fast as possible so that we can iteratively get to the finish line.